Future logicians, back to understanding a little bit more about logic. Here is on how to categorize deductive arguments and how to provide rebuttals that are quick and efficient. So how to categorize and rebut deductions is the topic. We're going to just start with reminding you of what the goal of logic is. The goal of logic is to preserve truth in inference. Ideally, if the premises are true, they offer complete or partial support for the truth of the conclusion. Whether they're offer complete or partial depends on what type of argument it is. So we're going to start with talking about deductive arguments. Here's an example of a deductive argument. No plants are tacos. Some green things are plants. Some green things are not tacos. You'll be learning much later in the semester how to use Venn diagrams like this in order to express simple claims, like in this case, no plants are tacos. In other words, nothing can exist between this overlap between plants and tacos. And there is something that is green and is a plant, so something exists between plants and green things. So when we consider what the relation between green things and tacos is, we find that there is something that is a green thing, but not a taco, outside of the realm of tacos, outside of the circle. Okay, so this is just giving you a visual diagram to consider the claims. You'll also be learning other ways to be able to deduce whether an argument is good or bad, given the standards of logic. Oop, went too far. There we go. So the two main types of arguments differ on the nature of the purported inferential link. Okay, so deduction, the purported inferential link is necessariness. Okay, so if the premises are true, it is necessary that the conclusion is true, is the inherent claim of the inferential link of necessary or deductive reasoning. Okay, so the conclusion must be true if the premises are true, is the idea. Induction offers what we call probabilistic reasoning. This is wherein if the premises are true, it offers partial support, not absolute or complete support, of the truth of the likelihood of the truth of the conclusion. A more precise way of thinking about the difference between deduction and induction is to think about the nature of the conclusions. So deduction is non-ampliative, whereas induction is ampliative. So ampliative means that the conclusion contains more information than the premises. So in induction, you learn more about the world if it is truth-preserving in inference, whereas with deduction, if you know what the value of the premises are, okay, then you can deduce the conclusion necessarily from that. So the deduction doesn't contain any more information in the conclusion than was present given just the premises. Deductions are evaluated as either invalid or valid. I'm always going to start with talking about invalidity, because that's what we test when we test deduction. We test to see if it's invalid. If it's not invalid, it's valid. So invalid means that an argument exists where it's possible for the premises to be true while the conclusion is false. So just that it's possible that if the premises are true, there's still a arrangement or possibility wherein the conclusion is false. That's an invalid argument. A valid argument is one wherein that's not possible. It's not possible for the premises to be true while the conclusion is false. Sound just means a deductive argument that is valid with all true premises. Thus, unsound means either it's invalid or it has at least one false premise or both. So we're going to go through some very basic types of deductions. We're going to start with argument by definition. So for this, structurally, what you'll often see is just one premise and one conclusion for an argument by deduction. And the entire inferential link just revolves around the words or phrases being synonymous. Okay? So it's based on the definitions agreed upon for the word. Look for synonyms in premise and conclusion. Again, look often for one premise and one conclusion. So Lily is a philologist, therefore she studies the development and history of texts. Second example, theft by legal definition requires intent to deprive permanently. Therefore, intention is necessary for stealing legally. So this is just operating from the definition to a necessary conclusion, given if that definition is true. Now, the next set are logical terms, okay? These operate in an agreed upon way. I like to think of these as functional words, okay? So one of the ways that they function is to categorize. So categorical reasoning is based on inclusion or exclusion from groups or categories, okay? Categories are just simply things that are similar or have properties in common, okay? So indicators of reasoning categorically include words like all, each and every, no, not all, some are not, only, and except. So here's a argument, a categorical argument. All humans are mammals. All mammals are vertebrates, thus all humans are vertebrates. Here's another example of categorical reasoning. No books are immense. Conclusion, all immense things are not books. So these are the key words you're going to look for indications of categorical reasoning, but also look for indications of categories as well. Now, I want you to conceptualize early on how these words function, because you use them intuitively often very well. We have what we call a natural deduction system. So we sort of inherited ways of thinking about this, and some of us are precise in our understanding of it, though we've never been given the terminology to explain it. So I want you to think for yourself. So this is active reflection. What do these logical terms mean? What does except mean? What about unless? And finally, all. How are they related to addition, subtraction, multiplication, division, or other mathematical ideas? So think for yourself. I want you to imagine and conceptualize how these logical terms operate or what they mean. Does not all mean the same thing as no? Explain. So that gives you an idea about categorical reasoning. Next, we're going to do disjunctive. A disjunction is simply an either or sentence, okay? Either here works like a both and, okay? So it's just an indicator of disjunctive reasoning. So normally it's just one single, what we call a disjunctive syllogism. So it's got two sentences, okay, that are premises and a conclusion. It goes like this: either A or B, not A, therefore B, or it could go the other way: either A or B, not B, therefore A. I hope I did the other one that way. So here's my example without using letters to substitute for concepts. Either you eat pie or cake, but you don't eat cake, therefore we can conclude you eat pie. For this, just look for the word or. We just don't have a lot of other words for that in the English language. That's a key word. And look for the word not, because the second sentence is a negation. But negation, we just mean literally uses the word not. Hypothetical reasoning is based on how a conditional or hypothetical and if-then sentence works. For example, if there are no clouds, it won't rain. There are no clouds, therefore it won't rain. Okay? This is a hypothetical syllogism, just as the other one was a disjunctive syllogism. It has two premises and one conclusion. Now, I want to get into conditional sentences a little bit before we move on, because these are very important to logic, and we'll spend a lot of time with them later. So I want to sort of investigate the nature of them a little bit. An if-then sentence, like if it rains tonight, then either the rain will leak, the roof will leak or the roof will hold. We have types of conditions here. We have both necessary conditions and sufficient conditions, okay? So what are these different types of conditions? A necessary condition is one that must be satisfied for a statement to be true. For example, if you're going to get your driver's license, a necessary condition for you to get that is for you to pass a driver's test. Another way to put it is if you didn't pass the test, you can't get your license, okay? Now, a sufficient condition operates a different way. It's one that, if satisfied, assures the statement's truth. So it's enough that if you meet this condition, then you find another statement to be true. So, for example, a sufficient condition for being an animal is being a dog. Okay? A sufficient condition for being an animal is being a dog. It's enough you're a dog to qualify you as being an animal. Now, it wouldn't work the other way, right? If you were a animal, that doesn't mean that's sufficient for you to be a dog. So I want you to practice this, and we'll return to these conditions later and just work through them when they pop up in our logical topics more. So this is your first time working with necessary and sufficient conditions. So fill in the blank with the correct type of condition, necessary or sufficient. Being 18 years old is a blank condition for being older than 16. Being at least 35 years old is a blank condition for being president. Okay, so let's do the first one. If you said being 18 years old is a sufficient condition, you are correct. It's enough that you're 18 to be older than 16, but it's not necessary. You could be 17, you could be 19, okay? Being 18 is a necessary condition for being older, but it is sufficient. Whereas being at least 35 years old is a necessary condition for being president. Now, try on your own. Being a possum is a blank condition for being a marsupial. And finally, being a mythical creature is a blank condition for being a unicorn. So which way does it work? Okay. Is the concept of marsupial inclusive of a possum? Okay. Or is the idea of a possum inclusive of marsupial? Okay. Finally, we have mathematical reasoning. This is based on mathematical relations. When we are talking, and logic really comes at the intersection of this, we can use language to represent reality. We can use other things. We can use music. We can use art. We can use filmmaking. But we can also use math to describe and represent reality. Okay? But often these two are related, but not quite clear what the relation between mathematical reasoning is and reasoning and language, okay? But where that overlap occurs, often this is where logical terms pop up because they operate in a similar way, logically, to mathematical relations. So if you see anything that's algebra, arithmetic, or geometry, then it's mathematical reasoning, most likely. So, for example, if a classroom must be redivided from 2 classrooms to 3, and given a desire for equal distribution of 24 students, one must conclude that each classroom should have 8 students. Here, if you're not sure if it's mathematical, check to see if you're doing the inferential link in your head, and it's a mathematical inferential link to see if it's mathematical reasoning. Again, a syllogism is a 2-premise, 1-conclusion deductive argument. Here's an example. If it is alive, it is made of carbon. It is not made of carbon, therefore it is not alive. Okay, this is an example of conditional reasoning again. Now I want you to practice conceptualizing these different types of deductive reasoning. It's either disjunctive, categorical, hypothetical, mathematical, or by definition. So one of those 5 types. If you're unsure, feel free to go back and look at the earlier indicator words and indicators of inferential links. If feet had wings, pigs could fly. If pigs could fly, I'd own a farm called Where Pigs Fly. Thus, if feet had wings, I'd own a farm called Where Pigs Fly. Next one. If I wish to withdraw from a class, then I'll complete a registration schedule change form. I will not complete a registration schedule change form. Therefore, I do not wish to withdraw from a class. Some cats are not gray. All gray things are colored. Ergo, some cats are not colored. A circle is not the same type of shape as a square. Though both are geometric figures, a circle is not a polygon while a square is one. Okay, next one. Again, your possibilities, math, definitions, categorical, disjunctive, or hypothetical. Bernie or Amir cook tonight. Bernie does not cook tonight, so Amir cooks tonight. All garlic is tasty. Some plants are not tasty, hence not all plants are garlic. Given that a citizen is a natural-born resident of a locale, and a denizen is an alien who is made into a citizen through some process, Tabor is a denizen of Spain, but not yet a citizen. Okay, next, if there was a hurricane, then there is no school today. There was a hurricane, therefore there is no school today. Because triangle A is congruent with triangle B and triangle A is isosceles, it follows that triangle B is isosceles. Next, Adele trespassed. So she intentionally entered someone's land or property without consent or necessity. Now, we talked a little bit so far about rebuttals, and we're just going to go over 2 very quick, sort of intuitive rebuttal methods. And by intuitive, I mean creative, okay? And by creative, I mean that you come up with an example that goes against an argument by either demonstrating that the argument has true premises with a false conclusion, given the way the argument is itself, or you can do what's called a counterargument method, wherein you create an argument of the same form to demonstrate that it's possible the premises to be true while the conclusion false. So these are rebuttal methods that offer quick ways to assess deductive strength by testing invalidity. So if you can find an example where the same structure of argument or the same argument can have true premises while you have a false conclusion, then you've demonstrated invalidity. Thus, this is not a good deductive argument. So let's talk about the counterexample method first. I just want to say you kind of intuitively do this when people make claims. So if I said something like all ravens are black, you might immediately want to look for a counter instance in the world, look for an instance or an example that is contrary to my general claim. So if you say, okay, well, here's an albino parrot, that's a counterexample method. You are demonstrating the falsity of the claim by saying, if this were true, then this particular conclusion would also be true, and it's not. The particular conclusion being this raven is also black, when this raven is not black, it's albino. Okay, so here, counterexample method, test to see if premises can be true while conclusion false by assuming the logically possible situation that fits. And this is where it's creative. You have to come up or create your own instance of when the conclusion is false and the premises is true. So here's an example. Argument, if it is a square, then it has 4 sides. And let's say it has 4 sides. So assume those are both true. The conclusion is, thus it is a square. So what you want to do is you want to assume it's true that if it were a square, it has 4 sides. And you also know it's 4 sides. But in this case, it's not a square. So one thing you can imagine would be a rectangle, something that has 4 sides, but isn't necessarily a square. I should say non-square rectangle there to be specific. So I want you to identify a correct counterexample. If there's a hurricane, then the school is closed. The school is closed, therefore there's a hurricane. So let's go through the possible ones. A, there is no hurricane, but school is closed for the holidays. B, there is no hurricane, but the school is closed because of flooding. C, there is a hurricane, but the school is closed because of flooding. A and B, or A, B, and C. Okay, I'm going to stop and give you the answer for this one, okay, to make sure that you understand why this is the case. If you picked D, A, and B, you are correct. Oops, clicked on it by accident. My apologies. Okay. So here we go. This is why. The conclusion says there's a hurricane. So in order to create your counterexample, you have to assume the falsity of the conclusion. So you have to assume there is no hurricane. Okay? But you also have to assume that first, if there is a hurricane, school is closed, which is okay because there wasn't one. And you also have to assume the school is closed. So in A and B, you assume both that there is no hurricane, so you assume the falsity of the conclusion while preserving the truth of the premises and coming up with a way that it makes sense that it could be the case, that's possible logically. Now, the counterexample method, I'm just going to introduce it here, but we won't use it necessarily as much as we will when we're actually working with deductive arguments in full later. This is just an introduction to deduction, and thus this is an introduction to a technique that we'll use throughout. So for counter-argument method, what we're going to do is we're going to look for the structure of the argument. And we're going to learn for different types of arguments, different structures. We call those structures forms. Sometimes we call them arrangements, but we can just call them forms right here, okay? So if we are doing a counter-argument, what we're trying to do is we're trying to look for the underlying form or arrangement of the parts of the argument. So here's an invalid argument that sounds valid, Okay, some fruit are green, some fruit are apples, thus some fruit are green apples. Okay, they're both green and apples. Because those three sentences are all true in the natural world, it's hard to conceptualize using that how it could be possible that an argument of this form has true premises but a false conclusion. So we're going to keep fruit in there, and we're going to switch green and apples to bananas and pears. So here, this is true. Some fruit are bananas. And it's also true some fruit are pears. Conclusion, some fruit are bananas and pears. That's false. So here we have the same arrangement of the parts. We could call it some A are B, some A are C, some A are B and C. Okay, that would be the way to do it to show the form, using letters to substitute in for the possible different terms. Given this term, I want you to create your own counterargument for this form using this idea: some x are y, some x are z, conclusion, some x are y and z. So the goal is to get a true premise, and then a false conclusion. Good luck with that. Again, this is creative work, and you might not hit it on the first time. That's okay. This is the, for me, fun part about logic, is to do creative conceptualizations. So given this lecture, you should be able to define and identify types of deductive arguments, define and identify validity, invalidity, soundness for deductions, define, identify, and create counterexamples and counterarguments, and define and identify necessary and sufficient conditions.